Good afternoon. Before we work some problems from chapter 2, some one-dimensional kinematics problems, we actually do need to talk a bit about vectors. Now, your book waits until the third chapter to formally present vectors and how they are used in physics, but we need a little bit of understanding about them in order to solve a few of the problems from your chapter 2 homework. So let's start with a review of a special triangle. You may have learned this in high school, or you should have learned this in high school. Here's a right triangle, meaning the corner there is a right angle. Laser pointer, please. This is definitely a right angle. And it's also an isosceles triangle. So this side is the same length as this side. And that means I can give these sides the same label. I will call them A, and I'll call the hypotenuse C. And Pythagoras showed us that A squared plus A squared is C squared for this particular triangle. Well, A squared plus A squared, we can just write as 2 times A squared. Let's now take the square root of this equation. It says that the hypotenuse, the length of the hypotenuse is equal to the length of the other sides times the 2th root of 2. 2th root, square root. I like to call it the 2th root since we say 3rd root, 4th root. All right, and that's something you should memorize. Anytime you're looking at a 45, 45, 90 triangle, and I know these have to be 45, right? Because the interior angles of a triangle in a plane always add up to 180. I've already used up 90 degrees. That leaves 90 left. Divide by 2, 45. Okay, so to go from one of the sides of a 45, 45, 90 triangle to the hypotenuse, merely multiply by the square root of 2. And you don't have to memorize this, but I find it useful to remember that the square root of 2 is approximately 1.4 in decimal form. Of course, it's an irrational number, so you need an infinite number of digits to represent that in a base 10 number system. Why are we talking about this? Well, we can use this in our brief discussion about vectors here. So here's a motorboat motoring over the surface of the water. And let's say that the motor produces a thrust force between the paddles on the motor and the water. Well, I skipped a slide. I meant to wait before I showed that shark. Yeah, so there's a force of 1,000 pounds of thrust developed between the motor and the water. It's kind of like, when you run, you push your foot against the ground here, the motor is pushing against the water. And then let's suppose this thing is also being pushed to the right by a great white shark, also with 1,000 pounds of force. I don't know if a shark can develop that kind of force, but probably close to it. And let's investigate an equivalent force that one could apply to this boat. So there are simultaneously 2 forces being applied, one to the right and one straight up. And obviously I'm using arrows to represent those forces. We will be using arrows often in this class to represent something that we call a vector quantity. And force, we shall see, is a vector quantity. Over here, I've redrawn the vectors and I've placed them tip to tail. See how this, over here, their tails are joined, and over here it's tip to tail. I have not actually changed the vectors because for our purposes, what defines a vector is its length and the direction that it points. So I may have drawn this vector in a different place on the screen than I drew this vector, but they have the same length and they point in the same direction, so they are the same vector. Well, now I'm going to close this triangle here with a hypotenuse. And based on what you saw just a moment ago, we can conclude that if the sides of this triangle, this vector triangle, each have a length of 1,000 pounds, then the hypotenuse must be approximately 1,400 pounds. So what I'm suggesting is that the simultaneous action of these 2 forces, 1,000 pounds each in the horizontal and vertical directions, is equivalent to a single force equal to this hypotenuse here. And the first time you're introduced to this idea, it may not be obvious. It certainly was not to me. Why should it be that forces act that way? Couldn't they add in some other way? Because what we're actually doing here is adding vectors. This is really the definition of addition of vectors. You place the vectors tip to tail, and then you join them to make a triangle like that. And this is called the sum of the 2 vectors. So I'm suggesting that you could, whatever motion this boat executes as a result of the motor force forward and the shark pushing to the right, the resulting motion will be the same as if you applied this single force off at 45 degrees, and that's supposed to say not 1,000 pounds. So let me fix that real quick. So if you were to push, forget about the shark, I should really remove the shark from the picture. If there were some other agent pushing at 45 degrees with the force of 1,414 pounds, the boat would move in a way that was identical to the original two forces being applied simultaneously. Again, not obvious, but a very important fact. I say fact because it's something you can actually confirm in a lab, and really you experience verification of that fact every day, all the time, because you ride in a car, you use any number of mechanical devices that were designed by people who had studied what we call Newton's laws, who had studied mechanics. And one of the basic facts of mechanics is that forces add like vectors. All right, moving on. Let's talk about how to resolve a vector into components, because you do have to do that for some of the problems in chapter 2. And before you can resolve a vector into components, typically you want to choose your axes. We need two perpendicular axes. They don't have to point vertical and horizontal. These axes do not, but they are perpendicular. So this would be a fine choice of axes, or these. Notice that the vector didn't change. If I go back and forth here, the vector didn't change, but my axes did change. Let's start with this one. Very often we will set up our coordinate system like this. One axis will be horizontal and the other vertical, but that's not necessary. So there it is. What I've just done is to resolve this vector into components. I have made a right triangle where the original vector is the hypotenuse. I think that's a good way of describing the resolution of a vector into components. You make a right triangle so that the original vector is the hypotenuse, and each of your components, the sides of that triangle, lie parallel to the axes that you've chosen. See how this component is along the x-axis, this component is parallel to the y-axis. That's it, and it's got to be a right triangle. Here's another example. So different set of axes, and that means that my components change, but the original vector has not changed. See, if I flip back and forth between these two, the original vector is the same. What has changed is the components, because I've chosen different axes. But in this case, it's still a right triangle. The original vector is the hypotenuse, and my two components are parallel to the axes. Yet another example. In this case, since the positive y-axis points in that direction, the y component actually points along the negative y-axis, which often is the case. So suppose we give this vector a name. Notice that I've written the arrow over the label A. That's to indicate that this quantity is a vector, not merely a number, also known as a scalar. So the arrow symbol emphasizes it's a vector. Now, if I had left off the arrow, if I had just written the letter A, usually that means we're talking about the length of the vector. You'll notice down here where I've labeled the components, they do not have the vector symbols. That's important. That's the convention we'll use in this class. When you're talking about the component of a vector, you don't draw the arrow, but you do put a subscript to indicate which component you're talking about. So if you see a letter with an X or Y subscript and no arrow, you're talking about one of the X or Y components of that vector. All right, well, the vector that we're concerned with at the moment is the acceleration vector, because that's the one that we'll be resolving in components in some of these homework problems from chapter 2. So here's a person who's jumped off a diving board. I just pulled this off Google. Kind of a cool photo. What city is this? I don't think this is Los Angeles, because I don't recognize that. And we know, we've talked about the fact that near the surface of the Earth, and until you get going at a speed where air drag becomes significant, your rate of acceleration, your rate of change of velocity is basically 9.8 meters per second, directed downwards. Is that still going to be true for something that's, let's say, rolling down a ramp due to gravity? In this instance, the reason this person is accelerating is because of gravity. When you roll a ball down a ramp, you're also looking at acceleration due to gravity, but is it still going to be 9.8? I think it's fairly evident that it will not be, but let's watch some video here. This man, Bruce Yaney, is, I believe, a retired high school physics teacher, but from what I could tell, he was an incredible teacher. He worked for many years, I'm assuming, at the same high school, but you can find dozens, if not hundreds, of videos of demonstrations on his YouTube channel. Some of his content might be described as lecture, but the emphasis is on demonstrations. I'm just in awe of how many quality pieces this guy produced himself, handcrafted. I think he built all of these. And here's what he calls some Galileo tracks, I think, where he explores the acceleration of some pool balls along tracks at various inclinations. So let's just watch a few seconds here.
How about if I try it from this side? And it won't do it from that side either. This piece was important because it was actually a piece that Galileo designed to help explain the idea of inertia.
So I highly encourage you, if you have the time, to check out some of his videos. But in the present moment, I think we can at least observe, I don't think that that billiard ball was really picking up speed at a rate of 9.8 meters per second. It was picking up speed gradually enough that you could really watch it, as opposed to when you drop something where it picks up speed fairly quickly. So if it's not speeding up at 9.8, then at what rate is it speeding up? That is the question that we seek to answer in this video. So here's a ramp or an inclined plane, and we will use the Greek letter theta, TH, not theta like the cheese, the Greek letter theta to indicate the angle of inclination there, how steep the ramp is. And let's put a brick on it. Maybe this is a polished stainless steel brick, gold, whatever, but it's got to be very smooth on the bottom because I'm going to imagine that it slides down this ramp without friction. Now, friction is a major topic in this class, which gets discussed in a lot of depth in chapter, or more depth, in chapter 5, I believe. So to help you visualize that, maybe you've greased the whole thing down with some silicone lubricant. So imagine that there's no friction whatsoever. And also notice that I chose a block, not a ball, because it turns out that a ball rolling down a ramp without slipping actually accelerates at a different rate from something that's sliding. And right now we're interested in the sliding acceleration. So I've drawn the gravitational acceleration vector. We know it points straight down towards the center of the Earth. I've labeled it G, but we know that G is just a special acceleration. It's that 9.8 meters per second. Now, this brick is not free to actually fall in the direction of the G field because the ramp is in the way. If there were no ramp, it would be free to fall parallel to G, but the ramp pushes back. And you've noticed that I've drawn the vector perpendicular to the two surfaces, where the two surfaces meet. It's perpendicular to that line of contact. Now, another word for perpendicular is normal. A line that's perpendicular to a plane is called a normal line, and that is why this force, the force of the ramp supporting the brick is often called the normal force, because it is normal to the surfaces. Don't forget the meaning of that word normal. It will really help you when you set up some of these problems. And now I'm going to draw G longer just to make this diagram clearer. But remember, if you were using meters per second, you know, whatever your scale was, like if you use 1 centimeter to represent 1 meter per second, this would have to have a length of 9.8. That's the significance of the length. It's equal to the magnitude of the acceleration. And now I have resolved that vector into components. Notice I've drawn a right triangle where the original vector is the hypotenuse because it's opposite the 90 degrees. And these components are parallel to and perpendicular to the ramp, which means what happened to my coordinate system? You know what? I had a nice graphic and it seems to have disappeared. So let me find that. Okay, I'm getting ahead of myself. The graphic's coming up. Notice that this component is parallel to the ramp, and this other component is perpendicular to the ramp. Now, there's a fact from geometry which is worth knowing for this class. If you have an angle and a second angle, and they intersect each other at two places perpendicularly, and you can see that here. This ray of the first angle intersects this ray of the second angle perpendicularly right here. Not here, this is not a right angle, but this is. Down here, the same thing. This ray of the first angle intersects this ray of the second angle, also perpendicularly. And if you can establish that fact for these two crossing angles, then you know that those two angles are equal. You could prove that using high school geometry. I have to think about that for a moment, but that's a fact that we need. If we go back to the diagram here, we can see that's what we're talking about, because here's one angle in question, the angle formed by the original vector and this component, and then there's the angle of the ramp itself. And you'll notice that right here, there's a perpendicular intersection of those two angles. And up here, there's a perpendicular intersection. I should have said the two rays. So they intersect orthogonally or perpendicularly at both places. And that's why we know that this angle must equal this angle. So I can go ahead and label that theta as well. If this is 20 degrees, this is 20 degrees. And a good mental exercise, I'm sorry I don't have a graphic for you. Another way to visualize that would be the following. Try to imagine what happens to these two components or to this angle as you decrease this angle. So if I let this ramp start to close down so that theta approaches 0, try to imagine how this picture would change. And after some thought, you may be able to see that this angle would also close down. And when this one goes to 0, this one would also have to go to 0. That's another way of saying or seeing that those two angles have to be the same. And there are probably other ways you could also establish the fact that these two angles are the same, but you need to memorize this picture because it's going to come up very often this semester. Block on a ramp, draw G, break it into components. That angle's got to be the same as the angle of the ramp. Okay, so now I've set up my coordinate system. In many problems, it's most convenient to put your x-axis horizontal and the y-axis vertical. But for this particular setup that we're looking at, it's actually easier or more convenient to put the x-axis parallel to the ramp. In this case, I've chosen positive as down the ramp, and the y-axis would be perpendicular. And that means I can give these components names now. This would have to be the x component of the g vector because it's parallel to the ramp, and this would have to be the y component, hence the labels. Subscripts indicate components, and notice I have not put a vector here, vector symbol, and I didn't put an arrow symbol here either. I suppose my G here just represents the length of the vector. So our task is to find G sub x, because you'll notice this is the component of gravity that could actually produce motion in the brick here. The brick is not free to accelerate in this direction. It's constrained by the surface of the ramp. It is, however, free to move in this direction. So if we'd like to know the rate at which this thing will pick up speed on its way down the ramp, we need to figure out how this component compares to the 9.8. And again, it's not obvious that this is the way it works, because in a moment we're going to do some math with triangles, in other words, some trigonometry. Nobody's born knowing that gravity works this way, that you can actually put something on a ramp at 30 degrees and draw a triangle here out of the g vector with this angle being 30, and then measure this side, and that's the actual acceleration of the block down the ramp. To really convince yourself that gravity works that way, you'd have to do an experiment. And I think indirectly you will be convinced of that with future experiments. But if we weren't on lockdown, we would do this in a classroom. Okay, so in order to do this simply, let's review some trigonometry, as I like to call it. Here's a right triangle with this particular angle being labeled theta. And instead of going with ABC, let's choose the letters O for opposite, because this side is opposite the angle that I've labeled. This side is adjacent, hence the label A, and then our trusty old hypotenuse. So we've got three sides here, and we're going to look at two important ratios. First, if you were to measure the length of this side and divide it by the length of the hypotenuse, that ratio has a special name. That's called the sine of the angle, abbreviated SI. So by definition, the sine of this angle is the length of the opposite side divided by the length of the hypotenuse. You remember SOHCAHTOA. You will be using a lot of trig in this class. Well, you're just using a few tools, but you're using them often. The cosine is a related quantity. This time you take the adjacent side and divide it by the hypotenuse. So this better be review for you. However, it's worth memorizing these two equations written in a slightly different form. Up here, let's solve this for O. Let's get the opposite side in terms of the other quantity. So move the hypotenuse over and you get this. And this is a really useful way of thinking about the sine function for this class. Because very often we're going to have a vector, which is the hypotenuse, and we'll know the length of that vector, but what we're interested in is the opposite side. And what this equation says is all you have to do, if you want the opposite side, is just take the hypotenuse, multiply by the sine function, and that gives you the opposite side. It's easy to remember, right? Because sine deals with the opposite side. Take the hypotenuse, multiply by sine of theta to get opposite. For cosine, if you're interested in the adjacent side, you would take the hypotenuse and this time multiply by the cosine of theta, and out would pop the length of the adjacent side. It's just the definition of those two trig functions as ratios, but it's written in a form that's more immediately applicable. So I would try to memorize those two. Later, we'll go back and do the same thing with the tangent function. So as an example here, suppose we've got a right triangle. This would have to be a 30, 60, 90 triangle. The hypotenuse is 24. You should be able to do this in your head. What's the length of the opposite side? Well, we take the hypotenuse, multiply by the sine of the angle. And one of the few trig ratios that I have memorized is the sine of 30. I know that that's 1/2. I think that one's worth memorizing. You see it often. What is this? This doesn't make any sense. How did I not catch myself here? This is supposed to say 12 without the degree symbol, right? Oops, let me fix that. Much better. One reason you couldn't have had degrees over here is the sine of 30. What is the sine? The sine of any number is always just a ratio. It has no dimensions. It's just a dimensionless quantity between -1 and 1. So when you take 24 and multiply by some ratio between -1 and 1, you're going to just get a number over here, no dimensions. That's why it didn't make sense to have the degree sign. Let's do that now with this picture. We can go back here. We are dealing with the right triangle. We do know the hypotenuse, it's 9.8. And we'd like to know this side, because this is, again, the component of gravity that's actually free to accelerate the brick. And you'll notice that this side is opposite the angle theta. So we can immediately apply the formula that we just looked at. The opposite component here, which I'm now calling g sub x, is the hypotenuse times the sine of the angle. Simple as that. Now, theta is a number that can vary from 0, let's say, that's if the ramp were just shut, so it wasn't a ramp at all, it was just a flat surface, or I should say a level surface. Or theta could be almost at 90 degrees, in which case this would be almost vertical. So what are the range of values taken on by the sine function when the argument, the input goes from 0 degrees to 90 degrees? That's this graph right here. This is a graph of sine of theta. Let me go back. I've actually taken the sine function and multiplied it by g. So what is the value attained by the sine of theta when theta equals 90 degrees? Sine of 90 is 1. 1 times g is 9.8. So really what I've done is scale up the graph of sine of theta by a factor of g. So the maximum value attained at pi over 2 radians or 90 degrees would be 9.8, not just 1. Okay, so here's a more extreme example where theta is approaching 0, and I've modified the vector diagram. You can see that the original vector is still the full 9.8, that's g, but that the component parallel to the ramp has now gotten very small. The y component is longer than it was previously. You can contrast that over here. Yes, they're both rather long components, but there's not a huge difference in the lengths of these two components. Now there is a very large difference. G sub x is almost 0. And that makes sense because as this ramp approaches being a level surface, you would not expect gravity to make this accelerate very quickly. Wouldn't it be weird if this thing started to pick up speed at 9.8 meters per second? We know that doesn't happen. On a surface that's nearly level, nothing should really slide at all. On the other hand, or on the opposite end here, how about an angle that's approaching 90? This looks like, what, 70, 80 degrees, maybe? 65, 66, tough to say. And now you can see that the y component is the short one, and the x component is the long one. Especially if you have not had much practice with this, it's kind of difficult to do this mentally, just to imagine these changes. So it really helps to draw a diagram, as I've done here. In fact, in the act of preparing this slide, I think I improved my ability to picture this in my head, how the components change. But you see how the component of gravity parallel to the ramp is now, this length here is almost as long as the original length, which is 9.8. That makes sense because if you actually were to tilt this all the way vertical, then this thing is just, it's brick. It's just going to free fall straight down at 9.8. 9.8. So I've indicated where we are on the sine function with a little dot here. We're approaching 90, whereas in the previous slide we were down here. Very, very physically reasonable, right? What happens when we actually get to 90 degrees? If I go back to, well, let's just use the graph here. If I actually evaluate the function at 90, then my acceleration parallel to the ramp would be the full 9.8, as I've indicated here, which we know must be the case. So it's not a linear climb. Notice how this graph is not a straight line that goes from 0, 0 to pi over 2 comma g. It's a sine function. Okay, and with that, we should be equipped to do some homework problems.